Hello everyone, my topic is one byte overflow in Chrome OS. I'm Yunsong Liu. Here is my outline. I will give you the introduction. I will talk about the flaw in C errors and the exploitation in Chrome OS. And finally, I will give you the conclusion. Okay, let's start. In September 2016, an individual programmer reported a Chrome OS exploit to Google. The report shows that user could execute code on Chrome OS from JavaScript as the root user by following in a sequence of necessary procedures. The issue was named CVE 2016-5180. I think it should be the worst possible exploit of Chrome OS. And actually, the bug finder got 100,000 US dollars for it. Let's go into the issue. C-Errors is a C library for asynchronous DNS requests. Here we just talk about one function in C-Errors. The function is called errors make query. The function takes a name string as input, allocates a memory area for the outgoing packet with DNS protocol data, and returns that newly allocated memory area and its length. Due to a logic mistake in the function, you could trick the function to allocate a too-short buffer by passing in a string with an escape dot. Here is one segment of the code. The for shows that we use the calculated length to allocate and fill a buffer. The loop at the to calculates the length of an escape's name. Included are the terminating dots to account for the length bytes. For n parts, there are n length bytes and either n or n minus 1 terminating dots, because the last part may or may not end with a dot. If it doesn't end with a dot, then an additional 1 is added to the length in the tree. There is a bug for the case when the last part ends with an escaped dot. The tree thinks that the last part ends with a dot and doesn't add a 1 to length. But since the dot is escaped, it actually belongs inside the last part and doesn't terminate it. So the last part doesn't have a terminating dot to account for its length byte, and the buffer is short by 1 byte. This causes the byte of DNS class to overflow the buffer. Another thing we need to know is that Chrome OS uses demalloc for managing the heap memory. Each time the program allocates memory, it will get a pointer back to the request memory region, and the demalloc will put a small header of its own just before that memory region. Look at the structure of the header. It has a pref size, forward, and back pointers. Because it's similar to what we learned in class, so I won't talk too much about it. Chrome OS runs an internal HTTP proxy which uses C-Errors. Because DNS class is a constant 1, we can write a 1 outside Chrome OS heap buffer by sending the right string to C-Errors. Okay, let's start our exploration. We have 6 stages. The first stage is called 820 hole. With the tricks of demalloc, we repeat allocating and freeing memory chunks. We can get a 820 hole in the memory. Here is the steps to get the hole. The red means we allocate a chunk, and the green means we free a chunk. Stage 2 is called out of bound write. Stage 2 is the most complicated stage. It triggers the single byte OOB write by C-Errors. First, a 1E0 chunk is allocated in step 10 to 12 by allocating 640. Then 1E0 and then freeing 640. Then the query buffer of errors is allocated into the 110 slot at step 13. This leaves a free 530 in the middle. Look at step 13. The 530 chunk has size 531, and the 1E0 chunk has prev size 530. The prev size field is only used when the previous chunk is free. Otherwise, the previous chunk spans the prev size field. This means that the size field of 530 immediately follows the query buffer in 110. The single byte that overflows the query buffer overwrites the size field of 530. Chunk size is corrupted from 530 to 500, as can be seen from the step 14. It triggers the memory corruption. Next, we come into stage 3. Stage 3 is named overlapping chunks. The 1E0 doesn't know anything about this corruption, and its prev size remains 530. Now the step 15 to 17 splits the free 500 into free 2E0 and in-use 220. But the malloc is already confused at this point. When it tries to update the prev size of the chunk following 220, it's off by 30 bytes from 1E0. And 1E0 believes that prev size is 530. It also believes that the previous chunk is free even though the 220 is in use. Now in step 18, 1E0 is freed. It tries to coalesce with a previous 530 chunk. There is a 2E0, where there used to be 530. The malloc is fine with that, and creates a large 710 chunk that overlaps the 220. Stage 4 is ASLR. Stage 4 is to break ASLR and to find base address of libc. It first turns the overlapping 220 into a more convenient 810 chunk. So it allocates the 820, which overwrites the header of 220 and changes the size to 810. The step 21 frees the overwriting chunk and the malloc finds it to be the size of 810. As shown in the picture, next we allocate to A0 to D0 and then free to A0. Now we use forward and back pointers to break ASLR. The 2 to A0 chunks have the same size and are placed into the same free list. With additional grooming at the beginning of stage 4, the exploit can be certain that the two chunks are the only ones in the free list. Well, there is also the third element linked in. The free list head allocated statistically from libc. So looking at the first two A0, its forward and back pointers point to the other two A0 and into libc. Also, the first two A0 overlaps with 820, which contains an HTTP header that is forwarded to an attacker-controlled HTTP proxy. So, that leaks two pointers that the proxy server forwards to JavaScript. The two pointers are used to calculate the address of 820 and the base address of libc. Stage 5 is place bind state into 820, and stage 6 is to run the root. The idea is to overwrite a bind state which holds callback information, a function pointer, and arguments. The function pointer is overwriting to point to system in libc, the base address of which is known, and the first argument is overwriting to point to a shell command string crafted into the 820 slot, the address of which is also known. Bind state chunk size is 40, so after we resize 810 to 40 in step 25 to 30, we reallocate 820 to corrupt the bind state to launch system in step 31 and 32. The callback triggers in 30 seconds, and the system runs a shell as root. No matter how limited or harmless a flaw may appear at the first glance, it could cause really terrible attacks to the system. Just fix any bugs at the first time. All the skilled hackers will find depths to exploit your system.